we're going to start out with 1.1. The section is called Introduction to Functions. The first thing that they talk about in this section is the idea of a relation. I've seen other textbooks call this a correspondence. What a relation or correspondence is a rule that relates two sets. Probably you have seen these before with the boxes and the arrows. The official terminology for that is called a map. So here's some boxes. And these boxes are going to have two sets. Let's have the first set, the input set, be a list of animals. This is the input set. And the output set will be a list of numbers. And the rule that's going to relate these two sets is going to be the life expectancy of the animal. So, totally making this up, but maybe we've got some animals, like we've got a lion, duck, dog, and an arrow is going to point at the number that's the life expectancy. So maybe the life expectancy of a lion is 7 years, and maybe the life expectancy of a duck is 10 years, and maybe the life expectancy of a dog is 12 years. So I've got a relation here, got an input set and output set, and I've got a rule that's relating those two sets. That's all a relation or a correspondence is. So what we are more interested in is a more specific type of relation, a function. So you've probably come across a bunch of different definitions of a function, but what they all kind of boil down to is that a function is a relation where each input corresponds with exactly one output. Relation where each input corresponds with exactly one output. So if I come back and look at this relation that I drew over here, this relation is indeed a function because each input points to exactly one output. So where things start to get a little bit murky is, what if I were to add another animal in here, like say a rabbit, and what if it also has a life expectancy of 10 years? Still a relation, still has an input and output, a rule that's relating the two sets, but doesn't meet this more rigid definition of a function. Does each input correspond with exactly one output? Yes, it does. A lion points at 7, a duck points at 10, dog points at 12, rabbit points at 10. It's okay that the duck and the rabbit are pointing at 10 because it does not break this rule. Each input is pointing at exactly one output. One of the ways that I like to think about this, that's going to come back in the future when we're learning about inverse functions, is I like the idea of a function does not have any ambiguity. There is no ambiguity. If I were to ask you what the life expectancy of a lion is, you look at the chart, you follow the arrow, you figure out what the life expectancy is. And even though duck and rabbit point at the same thing, there's still not any ambiguity. If I say what's the life expectancy of a rabbit, you look at the chart, you follow the arrow, the life expectancy is 10. There's no like, well, what if something, what like that's going to show up when it's not a function. So, for example, let's say that I had a list of people So the input set is a list of people, and the output set is some phone numbers. So if Joe has a phone number, and I don't want to get too crazy here with phone numbers, but Joe has a phone number. Maybe Sam has some other phone number. But Colleen has a cell number and a landline, a home number. Doesn't break any laws of physics. It's okay for Colleen to have two phone numbers, but does it break the rule for being a function? Yeah, because each input has to have exactly one output, and Colleen points at two different things. That's the evil two-headed arrow. I'm going to say that a lot when we're talking about functions. The evil two-headed arrow is something that breaks this. This is not a function. And if we're going to think about it, when I was just talking about this ambiguity, if I ask you what is Colleen's phone number, here's where the ambiguity shows up. Well, do you want her cell phone number? Or do you want her home number? Which one are you talking about? So the evil two-headed arrow has that ambiguity, and it breaks this definition of a function, not a function. Still a relation, and still can make sense in real life, but it doesn't fit that more stringent definition of a function. Alright, so I've got a little made-up function here, and I want to talk about vocabulary. I've been using the words input and output to talk about these two sets. Some more official vocabulary is the input. The set of all the inputs is called the domain, and the set of the corresponding outputs is called the range. When we're doing graphs and more algebraic kind of stuff, the domain is typically our x stuff, and the range is typically our y stuff. All of the x's and all of the y's. There's a couple other vocabulary words I want to point out. These are probably not as commonly used, but I super like them for story problems. The domain, the x stuff, the inputs, these variables are called the independent variable. The output is the dependent variable. So if you're thinking of like a graph or something, or a function, when we get into the function notation, here's a function. I input x and I output y. So if I input 3, for example, 2 times 3 is 6, plus 5 is 11, I output 11. 11 depended on what 3 was. The y value depends on what I plug in for x. So the y variable, the output variable, is the dependent variable because it depends on what you plug in for x. Not that that's such a huge deal, but in story problems it can be kind of nice when we're trying to figure out what quantity to be the x quantity and what quantity to be the y quantity. Like if we're talking about the cost of, say, a taxi ride. Does the cost of the taxi ride depend on how many miles you drove, or does how many miles you drove depend on the cost of the taxi ride? Like which one depends on which can help you set up which quantity should be the input, the domain quantity, which quantity should be the output, should be the range quantity. So that's kind of nice. Those vocabulary words can kind of help sort that out. Okay, so the next big topic is trying to decide if something is a function or not. So we've been looking at these maps, and these maps have been like a pretty visual way to decide if a relation is a function or not. So really what we're looking for is there an evil two-headed arrow? If two inputs point at one output, that's cool, because the definition said every input has to correspond with exactly one output. That's no big deal. But what is a big deal is if an input points at two different outputs, that evil two-headed arrow I was talking about. So that evil two-headed arrow is a nice visual way to see that a map of a correspondence of a relation is not a function. It breaks that rule of every input has to have exactly one output. So unfortunately, maps are not the only way that we're going to look at functions, and we've got to look at some other ways to recognize things that are functions or things that are not functions. Some typical math examples are some little sets, and I say little because they're little enough to write instead of being infinitely large. In math, a curly brace means a set, and so we're going to have a set of some ordered pairs. So this set has the ordered pair -2, 1, 1, 3, 1, 4, and 3, -1. So this is a relation. It's got a whole bunch of inputs. These first numbers are the input numbers, and the second numbers are the output numbers. So we've got a relation because we've got some sort of rule. I don't know what the rule is. I mean, I guess this is the rule. -2 always goes with 1. 1 always goes with 3. That's the rule. But does this rule, does this relation fit the more stringent definition of, is this a function? And the answer is no, this is not a function, because if I were to draw this looking like one of these maps, 1 would be over here, and it would have the evil two-headed arrow. 1 would be pointing at 3, and 1 would also be pointing at 4. This is not a function. Every input has to have exactly one output, and this one happens to have 2 outputs. So this is not a function. Not quite as easy to recognize visually, maybe as just a blatant two-headed arrow sitting there, but it's the exact same idea. This would make a two-headed arrow if we were drawing a map. Let's look at this other example. Here's this set of some ordered pairs. We got -2, 1, 1, 3, 2, 3, and the last one is 3, -1. So is this set of ordered pairs, this relation, is this a function? Yes, this one is a function. This time, we've got no evil two-headed arrows. If I was going to draw this like a map, -2 would point at 1, 1 would point at 3, 2 would also point at 3, but we've talked about how that's okay, and 3 would point at -1. Each input has exactly one output, so it fits the definition of a function. All right, so far we've looked at maps, and we've looked at these sets of ordered pairs to try to determine if the relation that they've given us is a function or not. We're looking for the evil two-headed arrow. Frequently, we're going to have to be able to do the same thing graphically. So let's say, for example, we had the graph of a circle. Here's the graph of a circle. And what we're going to do to determine if a graph is a function or not is we're going to use what's called the vertical line test. Vertical line test. So let's just say, for example, here's a point that's 2, or an x value that's 2, and this point up here then would be 2. Let's say this is 2, 3, and let's say this point down here is 2, -3. So what I'm getting at is if I was writing an XY table or those input-output map things, 2 is corresponding with 3 and -3. This is the evil two-headed arrow we're looking for. So the vertical line test lets us find that really quickly without drawing this stuff. If I were to draw a vertical line through a graph, that wasn't very vertical. If I were to draw a vertical line through a graph and it hits the graph at more than one point, that is a real quick way to find the evil two-headed arrow. So some of the graphs that you are supposedly familiar with at this point, say something like a line, a y = mx + b line, no matter where I draw a vertical line here, it's only going to ever hit this line once. So a line is a function. Every input has exactly one output. You probably graphed before some parabolas. Here's a parabola. Anywhere I draw a vertical line, it's only going to hit that graph once. So this is a function. It passes the vertical line test. We're going to run into some shapes later this semester in Chapter 5. One of the things we're going to run into is a sideways parabola. Sideways parabola, it's still a relation. We're going to have an equation that graphs and makes this sideways parabola, but it's a perfect example of something failing the vertical line test. If I were to draw an XY table here, whatever this X value is, it's pointing at 2 different Y values, whatever this positive one is and whatever this negative Y value is down here. evil two-headed arrow. Earlier we were looking at these two relations to decide if they were functions or not. I can do the exact same thing we were just doing, that vertical line test, if I wanted to think about these graphically. So here's -2, 1. There's a point. The point at 1, 3. There's a point at 1, 4. And there's a point at 3, -1. So even though these aren't curves, like the last couple examples I was looking at, this graph still can be interpreted as a function or not using that vertical line test. So the vertical line test says that if I can draw a vertical line anywhere that goes through more than one point, it's failing the vertical line test and it's not a function. Graphical way of finding that evil two-headed arrow. Same thing for this example. If I were to interpret this graphically, here's -2, 1, here's 1, 3, here's 2, 3, and 3, -1. And anywhere that I draw a vertical line on this graph, it will never pass through more than one point. So it passes the vertical line test, and it's a function.